We're going to go over section 1.3, matrix arithmetic. Whenever we talk about matrices, we're going to use capital letters. For example, here's a matrix, A, capital A, and it has M rows and N columns. When we label the entries inside the matrix, we're going to label them as lowercase a 1, 1, 1, 2, and so on. And the number here corresponds to the column, and the first number corresponds to the row. So you can see all of these are in row 1, so I have a 1 here. And all of these are in column 1, so that's where this 1 comes in, the second number beside this A. So this is a M by N matrix. And we're going to write the order of the matrix like this. We say M by N. And sometimes you can just write it like this. With the capital A and in subscript here you have M by N. So let's give an example of a 2 by 3 matrix and a 4 by 1 matrix. So let's say A is a 2 by 3 matrix. So that means it has 2 rows and 3 columns. So an example would be something like this. You see 2 rows, 3 columns. And let's give an example of a 4 by 1 matrix. So we'll have 4 rows and 1 column. So we can say that this matrix B is a 4 by 1 matrix. Now when we have such a matrix where it has 1 column, we call it a column vector. Or you can say a column matrix. But usually you'll see column vector. And we're going to learn more about vectors later, but from now on, when we see a matrix like that's just a column, think of it as a column vector. We can also talk about a matrix C. Let's say it is 1 by 5. This will be called a row matrix, or a row vector. We're going to actually use row vector more often. And C would be something like this, where we have 5 entries. Now sometimes you'll see commas in between the entries, just so we know that these are different numbers. Like if you don't see a comma and they're kind of close together, you might think it's 37 instead of 3 and then 7. So just be careful with that. Okay. Another way we describe a matrix is we say that A is equal to its entries Aij. So this is just a common form of a matrix. So we say that A is equal to parentheses Aij and B is equal to parentheses Bij. So capital letter for the matrix and lowercase letters to represent the entries inside the matrix. So when are 2 matrices equal? Well, 2 matrices are equal if they have the same order, which means the same size, and every entry in each matrix is the same. So 2 matrices are equal. Let me write this down. If they have the same size. So in other words, A is an M by N matrix, and B is also M by N. And each entry in A is equal to each entry in B. actually I'm going to put each entry Aij is equal to each entry Bij. Let me give you an example. So if we have the matrix A is 3, 2, 2, 1, 0, 8, and the matrix B is equal to 9, 4, 2, 1, 0, 8. These matrices are not equal. They have the same size. They're both 2 by 3 matrices, but this number is different from this number. So for them to be equal, they have to have exactly the same entries. So you could say something like A is equal to 2, 4, 1, 3. B is equal to 2, 4, 1, 3, 0, 0. These matrices are not equal. Although we have the same entries, 2, 1, 4, 3, 2, 1, 4, 3, these matrices are not the same size. This is a 2 by 2 matrix, 2 rows, 2 columns, and this is a 2 by 3 matrix. They have to have the same size, and you can see that this 0, 0 does not appear over here in this matrix, so they're not equal. The only time they would be equal is if you see exactly the same thing for A as B. Okay? Let's talk about scalar multiplication. Let's say you have a matrix A that's an m by n matrix, and you have some scalar. What I mean by scalar is it's just, you can think of it as a real number or a complex number. So alpha here is a real number. So you can write it like this as well. Alpha belongs to the real numbers, and it depends on what field you're working with. In general, you can just think of real numbers. That's the field we're usually going to work with, but sometimes we can work with complex numbers. So if it's not specified, assume that we're working with the real numbers. Okay, and what I mean by complex numbers is that you involve the imaginary number I in the number. So something like 3 plus 5i. Also, just 3 is a complex number. The complex numbers include the real numbers. But when we're talking about real numbers, there's no imaginary part here. You can review that if you want. So, how do we multiply a matrix by a scalar? If we have a number outside of a matrix, all we do is we send that number into every entry. So this is going to be equal to alpha times Aij. So you have this big matrix with a number outside of it, so you send that number to every single entry inside the matrix. Let's look at an example. So here I'm taking this 3 by 3 matrix and multiplying it by the number 3. So according to this definition, I'm going to send this 3 to everything inside the matrix. Let's do that. So this is going to be, I'm going to write it out very explicitly, and then I'm going to reduce it. I just want to make sure you see what I'm doing. Okay, so just like it says here, every single entry gets multiplied by this number 3. So we're left with 6, 3, 0, 12, negative 3, negative 3, 0, 0, 3. Okay, that's pretty simple. Let's talk about matrix addition. Suppose you have two matrices, A and B, and the matrices are both the same size. This is very important. They have to be the same size to add them. And we're going to label the entries inside of A as lowercase aij and the entries inside of B as lowercase bij. You can add these two matrices, and what you're going to get is a matrix C, where C is also m by n, and C is equal to Cij, where Cij is just the sum of Aij plus Bij. And this is going to make complete sense. You're just going to add each entry. Let's do a quick example. So here is a 2 by 2 matrix, and here's another 2 by 2 matrix. I didn't label them A and B, but they're just two matrices. You can call them A and B if you want. Let's add them. So like it says here, for each entry, so if we go with the 1, 1 entry, we're going to add A11 plus B11. So I'm just going to add this one to this one. If I want the 1, 2 entry, which would be the second piece, you would do 2 plus 0. So 1 plus 4, 2 plus 0, 3 plus a negative 2, and then 4 plus 1. So you're left with 5, 2, 1, 5. And that's it. So I might ask you something like, what is C21? What is that entry if this is A, this is B, and the sum is equal to C? Well, you would say, oh, this corresponds to the row, and this corresponds to the column. So it's in the second row, first column, and so the entry C21 is just equal to 1. Okay, let's do another one. Let's add these two matrices together. Here I have a 2 by 2 matrix. We're going to call it A. And this is a 2 by 1 matrix, and we're going to call it B. You can see there's a problem because we don't have anything to add to this 2 and this 4 in this matrix. Remember the definition for matrix addition. When we want to add two matrices, they have to be the same size, m by n. So this matrix is 2 by 2, and this matrix is 2 by 1, so we cannot add them. So here you can just say that this does not exist because you can't add the two matrices together. All right, the next topic is matrix multiplication. This is a little bit more complicated than matrix addition and scalar multiplication. So remember, scalar multiplication was when we had a number on the outside of a matrix and we were multiplying those two together. Matrix multiplication is when we have two matrices and we want to multiply them together. What we're going to do is we're going to start by defining it for a row and a column vector. So to start, let's say you have a row vector times a column vector. Let's say your row vector is A, 1 by n, and your column vector is n by 1. And you want to multiply these two matrices. So something you'll see in your book is that when you have a row vector or a row matrix, you're going to write this matrix, instead of this capital A, they're going to write it like this, an A with an arrow on top, but they're going to bold this A. And when you see a column vector, they're going to write this as a lowercase b, but it's going to be bold. So the way you can tell the difference is you'll have an arrow, meaning it's a row vector, and without the arrow is going to be a column vector. I'm going to show you this as an example, and then I'm going to give you the definition. So for example, let's say we have 1, 0, 5, 2. This is a 1 by 4 row vector. let's make this bold. And then let's say that B is 2, 2, negative 1, 0. And this is a 4 by 1 column vector. Okay, notice that when I was giving this definition, when we're multiplying them, I used in here and I used in here. That's what we're going to do whenever we have a row vector and a column vector and we want to multiply them. If these numbers are not the same, then we cannot multiply the row vector with the column vector. So here I have a 1 by 4 row vector and a 4 by 1 column vector. When we multiply A times B, what we're going to do, so let's put it over here, 1, 0, 5, 2 times 2, 2, negative 1, 0. We're going to take the first entry in the row times the first entry in the column, so 1 times 2, then plus the second entry in the row times the second entry in the column, 0 times 2, plus the 5 times the negative 1, plus the 2 times the 0. Okay, so let's simplify this. This is 2 plus 0 minus 5 plus 0. We get negative 3. So we got a 1 by 1 matrix. We just didn't add the parentheses, but you can say this is negative 3 like this. But it's 1 by 1. And this is also called the dot product. I'm sure you've seen the dot product before. So what you get when you multiply A times B, you get a matrix C, which is going to be 1 times 1. So you're going to take this number, and you're crossing out these two. So these two have to be the same, and then what you're left with is this 1 times 1 here, okay? So that's how you multiply a row vector with a column vector. Now there's a reason I'm going to do this, because I'm going to expand this for all matrices. Okay? So from there, let's talk about what happens. Oh, and also I want to put this in summation notation. So when we have, so notice I took this is the entry A11, A12, A13, A14, right? Because we called this the row vector A. This is our column vector. I'm going to erase this so I can write what I want out. This is our column vector B, which we're going to put in bold. And the column vector is B11, B21, B31, B41, right? That's how we define matrices. Remember, the first number corresponds to the row and the second number corresponds to the column. So what we did was we took A11 and multiplied it by B11, A12 with B21, A13 with B31, and A14 with B41. So now I want to do this in general, because we can have a row vector that's 1 by 9 and a column vector that's 9 by 1. So I want to give you the definition in a more general way. So if A is 1 by n and B is n by 1, then multiplying A with B is a 1 by 1 matrix, and this gives us the sum from I is 1 to n of A1I times BI1. I'm going to move this down. Put in green. I don't like how I wrote that A and the B, so let me fix that just a little bit. Okay. Which is exactly what we did a minute ago. Let me write it out. A11, A12, dot, 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 all the way to A1n times B11, B21, B31, all the way to Bn1. If we multiply these two matrices, this row vector with the column vector, how we did it last time was we said that A11 times B11. So we started with 1 here and a 1 here. That's exactly what the summation says. Start with 1, so it'd be A11 times B11. Then plus, when I is 2, it'd be A12 times B21. So A12 times B21. And then so on, all the way to A1n times Bn1, which would be the last two things you need to multiply. Okay? All right, now let's talk about extending this to any two matrices A and B. How can we multiply not just row vectors with column vectors? So let's scroll down a little bit. Actually, I'm gonna have to make some room. Okay. So let's say A is an m by n matrix and B is an n by p matrix. Then we can multiply these two matrices together. And A times B is the matrix C, where C is m by p. Okay, so what's happening is these two numbers have to be the same in order for us to multiply A and B together, these two matrices. And what we're left with is an m by p matrix. Okay, so that's where I got the m and the p. So these numbers can be the same as n, they can be different. These two numbers do not have to be the same. The only thing is these two numbers have to be the same. The number of columns in A has to be equal to the number of rows in B. Okay? So C is m by p, and C, which is equal to Cij, where Cij is equal to the row AI times the column Bj, which is equal to the sum, I is 1 to n, of AI, actually this should be the sum k is 1 to n of Aik times Bkj. I'm going to explain this to you in just a second. Okay, so this AI is the row I in matrix A, And this is the column vector J in B. Okay. So let's see this real quick. Make sure you copy that down. So we can think of the matrix A, which is going to be, we said was an m by n matrix. Well, since it has m rows, we can think of it as a bunch of row vectors. And this just means all the way to a m. And each one of these row vectors contains n entries. Let me give you an example just so you understand what I'm doing. Let's say A is 3, 1, 6, 0, 2, 4, 8, 1, 9, 9, 0, 0, 1, 1, 3, 3. This is a 4 by 4 matrix. I can think of this 4 by 4 matrix as 1, 2, 3, 4 rows. So here, this M is the number of rows we have, right? So I'm thinking of it as a matrix that has 4 row vectors, and each row has 4 entries that corresponds to this number here. So for any matrix A that's m by n, it's going to have m row vectors and n entries in each row. Now we can think of B, which we're going to say is an n by p matrix. We can think of that as a matrix with p column vectors, right? So if B was equal to, let's say, 1, 1, 3, 2, 2, 7, 0, 5, 9, and 6, 1, 2. Let's say this is the matrix B. Well, you can see I have 3 columns, so I can think of it as a matrix with 3 column vectors. This matrix is a 4 by 3 matrix, and each column has 4 entries, 1, 2, 3, 4. Okay, so for a random matrix that's n by p, it's going to have p columns and n entries in each column, corresponding to this number here, just like I have here. Okay, so when I gave you this definition, what we're going to do for each entry in our matrix C, when we multiply these two matrices together, the entry, let's say C1, 1, is going to be taking row 1 in A and multiplying it by column 1 in B. And if we want row 1, that's going to be here. This I is going to be 1, and column 1, that's the J here. Then we're going to sum up just like we did it a few minutes ago. When we take row 1 with column 1, we take the first entry in the row with the first entry in the column, and then add it to the second entry in the row times the second entry in the column. I'm going to work through this. Just make sure you write this definition down and think about it, and maybe return back to it after we do an example. See if you can understand the meaning behind each piece. I think it's easier to see how I do it than to understand this definition. It seems kind of complicated. So let's go through an example and then make sure to go back and see if you can understand what I've written here. Okay. I want to multiply these two matrices. I want to find A times B for A is this 2 by 2 matrix and B is this 2 by 2 matrix. Okay. So first off, I want to figure out the size of A times B. So A is 2 by 2, and I'm multiplying it by another 2 by 2 matrix. What was the rule? This number has to be the same as this one, which it is. Cross it out. The matrix we're going to be left with is going to be a 2 by 2 matrix. So this is going to be the matrix C, that's 2 by 2. All right, so the matrix C is going to look like this: 1, 1, C1, 2, C2, 1, C2, 2. Now we need to figure out each one of these entries. I'm going to do that by rewriting these two matrices together, like this. And let's follow the rule. For this first entry, what I'm going to do is I'm going to take row 1 of matrix A and multiply it by column 1 of matrix B. So I'm going to take row 1 and multiply it with column 1. Okay, how did we do this before? We said 2 times 4 plus 1 times negative 2. Add these together, that will be C11. Okay, let's delete this. Let's move over to C12. C12 is taking row 1 in A and multiplying it with column 2 in B. So we ignore everything else and just multiply this row with this column. So what do we get? I'm going to put a line here so I don't mix up my sums. So we have 2 times 4 plus 1 times 3. 2, 4, 1, and 3. Okay. Now let's figure out C21. So C21 is taking row 2 in A and multiplying it with column 1 in B. So 3 times 4 plus 0 times negative 2. Okay. Now let's figure out C22, which is taking row 2 in A and multiplying it with column 2 in B. So we get 3 times 4 plus 0 times 3. Now let's simplify this. We're going to get 8 minus 2, so that's 6. 8 plus 3, that's 11. 12 and 12. And we're done. This is the matrix C that corresponds to A times B. Let's try another. Here I want to multiply A times B, where A is a 2 by 3 matrix and B is a 3 by 4 matrix. First off, we need to see if A times B is even defined. So A is 2 by 3, 2 rows, 3 columns. B is 3 by 4, 3 rows, 4 columns. These two numbers are the same, so we can multiply, we cross them out, and what we're going to get is a matrix C that's 2 by 4. I'm going to write out this matrix. It's going to be C11, C12, C13, C14, C21, C22, C23, C24. Again, 2 by 4. So we're going to have quite a bit of entries to figure out. So let's multiply them. I'm going to put both matrices down here so we can multiply. This is 1, 3, 2, negative 1, 1, 4 times 1, 0, negative 1, 2, 1, 2, 1, 1, 4, 3, 2, 6. Okay. Let's see what we get. We're going to start with the first entry. Okay, so C11, we take row 1, multiply it with column 1. So 1 times 1, get 1, plus 2 times 0, so 0, 1 times negative 1 is a negative 1. Okay, I'm going to put a line here so I don't get confused. So that gives me this entry. I'm going to go ahead and cross it out. Let's erase this. To get C12, I need to take row 1 of A with column 1 of B. So 1 times 2, which is 2, plus 2 times 1, which is 2, plus 1 times 2, which is 2. Okay. I need to make this a little bit smaller so I can put it all in one section here, so you can see it. Okay. Maybe a tiny bit smaller. Great. Let's go to the next piece. I need to figure out, because this one's done, what's C13. So that's going to be row 1 times column 3. Here's column 3. 1 and 1 make 1. 2 times 1 is 2. And 1 times 4, that's 4. Okay. Did this one. Now let's do 1, 4. So we take this row, multiply it with this last column. So we get 3, 4, and 6. Okay, so now we've finished up the first row of C. Let's figure out the second row. So we're going to do the same thing. We're going to take row 2, and to get this one, we're going to just multiply it with column 1. So we're going to have 3 plus 0 minus 4. Okay, to get the next one, we take row 2 and multiply it by column 2. So we get 6 minus 1 plus 8. Okay. Then row 2 times column 3 will give us 3 minus 3 plus 16. All right. And then row 2 with column 4 is 9 minus 2 plus 24. Let's clean this up. So we get 1 minus 1, which is 0. Then we have 2, 2, and 2, that makes 6. So I'm going to cross these out. 4, 6, 7, 13, negative 1, 13, 16, and then 31. Let me just check this last one here. I think I might have made a mistake here, right? Yeah, I think this one right here is a negative 1. Let me go back just a second. When I figured out this entry here, I took 3, yeah, that's a negative 1, and that's a 16. So this should be 18. Okay, and so we've figured out matrix C, which is A times B. Great. I want to do one more example that's really a non-example. And I want to show you what happens, why we can't multiply these two matrices. So here I have a matrix A and a matrix B. A is 2 by 2. B is 3 by 2. 1, 2, 3, and 2 columns, yeah. So these two numbers here are not the same. So if I asked you to multiply these two, you would say, oh, this does not exist because these two numbers aren't equal, and so we just cannot find the multiplication of these two matrices. But let's say you forgot to check that. What would happen? Well, let's put the two matrices here. 1, 2, 3, 4, and 3, 2, 1, 1, 2, 7. I want to multiply these two. So my first entry in this matrix, let's say maybe I say, oh, this is going to be a 2 by 2 matrix because I have this number and this number. But the first entry, the 1, 1 entry, is going to correspond to taking row 1 and multiplying it with column 1, right? So you get started and you say, oh, 3 times 1 is 3, then plus 2 times 2, which is 4, but then you don't have a third entry here in this row, and you have one here, and that's where you're going to see that, oh, I can't actually multiply these two matrices. So when you don't have the same number of entries in the row as you have in the column, then you can't multiply them. So this would be a question mark because you just can't actually multiply them together. So you would say does not exist. Let's move on. Let's talk about the transpose of a matrix. So a matrix A, that's m by n, it can be any size. We can write it in this form. Remember, A is equal to lowercase aij. The transpose of the matrix is just flipping the matrix along its diagonal. So it's going to look like this, AJI. So whatever went in the 1, 1 spot also goes in the 1, 1 spot. Whatever that was in the 1, 2 spot goes to the 2, 1 spot. I'll show you what I mean. Let's look at a few examples. So here I have A is equal to 1, 2, 3, 6, 2, 8, and I want to find A transpose. Well, A transpose, I didn't write it here, but A transpose is an n by m matrix. So maybe you should jot that down. We started with an m by n, now it's going to be n by m. And we just, look, you see how I had an ij? I just switched these two. So this is a 3 by 2 matrix. What we're going to have is a 2 by 3 matrix. So 1, 2, 3, 1, 2, 3. Okay? What was in the 1, 1 spot goes in the 1, 1 spot. What was in the 2, 2 spot goes into the 2, 2 spot. This is in the 1, 2 spot because it's in the row 1, column 2. These two are going to be flipped. This is now going to go into the 2, 1 spot. So what I'm doing, this might actually be helpful for you, is I'm making like a diagonal line here, and whatever is over here, I'm flipping it down here, and whatever's here is being flipped up. So let's continue what I was saying. This is in the A1, 2 spot, so now that goes to the A2, 1 spot, which is right here. This is the 2, 1 spot. This is in the 2, 1 spot, so A2, 1 now goes into the A1, 2 spot. So this goes to 3, this is 2, and this is 8. So this one was in the 3, 2 spot, so it goes into the 2, 3 spot, right? You can see this was A3, 2. Now it goes to A2, 3. So A2, 3 is right here. Do you see how these have been flipped up here? So if I drew a line here, you could see they're flipped up here, and this 2 is now down here. But let's erase this line here because we don't really need it. Let's try another one. Here I have a completely square matrix. This one's actually probably the easiest one to see. I'm going to draw a diagonal line right here because these are the things that have the same row and column number. So if I want to find B transpose, we keep the things on the diagonal the same. So this is 1, 5, 9, but whatever's here is now flipped here, and whatever was here is flipped down here, okay? So this becomes 4, 7, 8, and this is 2, 3, 6. Let's make sure I did this correctly. This is the 1, 2 spot, so now it goes to the 2, 1 spot, which is correct. This is the 1, 3 spot, so it should be sent to the 3, 1 spot, which this is the 3, 1 spot. This one is the 2, 3 spot, so it should be sent to the 3, 2 spot. So 1, 2, 3, 2. Okay, and you can see that this is exactly flipping this down here and this to the top. So this is the transpose. I think I have one more. Yeah. So here I just have a row vector, and I want to find the transpose of this matrix. So what is C transpose? Again, the diagonal would look like this, okay? Whatever is here, you're going to flip it along this diagonal. So it's going to become a column vector. If this stuff is confusing to you, I think the best thing to do is write what entry it is. C12, C13, and C14. So if you ever just can't visualize what you need to do, just remember this needs to go to this C21 spot, this needs to go to the C31 spot, and this needs to go to the C41 spot. So you can see all of these would become in one column. So we get 1, 1, 2, 4.